So if we go into peer analysis, talk about fuzzy scoring. So this is type 1 fuzzy logic, and I'll give you an example here. So this would be one feature. This is an example of a dental procedure. So you go to the dentist, procedure code 01204. I believe that's just a basic visit to the dentist. And so we calculate a feature for each of the peer group for all dentists. We create a peer group of all dentists, and we count how many this features, how many times did each provider use this procedure code over the course of a year. So we can see on the horizontal axis, the number of providers that used it one time versus did it 351 times in the year. And if we plot a curve, which just is a percentile curve, we can say, well, the number of providers that used it once looks like about 150 as the score. So the way this vertical axis is set up, it's a percentile curve. So this cumulative percentile, we can see 164 times, that's the 99.813 percentile, whereas one would be a score of 150, so about the 15th percentile. So this is one type of fuzzy curve. We can map a feature value, the number of times a dentist has used this procedure code in a year. We can map that, comparing it to all dentists, and assign a percentile score and saying, if you've used it 164 times, you are in the 99.8th percentile, or in a score out of 1,000, you have a score of 998 out of 1,000. And that would be an outlier compared to the vast majority, where 95% of dentists have used that far less. So this is how we can translate a feature value into a new domain or a new dimensional space, which is this fuzzy logic score. And we can map feature values using a curve like this to percentile scoring curve, or in other case, we use different scoring curves. We use curves of these shapes. Could be a growth curve, which would be kind of like a logistic or a hyperbolic tan curve, where we can say a high value is suspicious. Like the previous example was a growth curve. A high number of general examinations is suspicious, or a high number of teeth extractions is suspicious, or a high number of prescriptions is suspicious. So you can say low is not suspicious, high is suspicious. It could be a kind of logistic curve or a hyperbolic tan curve there in the top left, and it could have asymmetric. You could decide where the min, mean, max is, and we can assign 3 parameters to the curve. You could assign a left value, where does the minimum start, a right value, which is where's the maximum score, and a midpoint, so where's the point of symmetry, or where's the 50th percentile score. So there's 3 parameters you can use to create the score, and we can assign these parameters to the actual distribution of the data. So we can say, let's make the left value the minimum, the right value the maximum, the mid value could be the mode or the average or the median, or we can make the left value the average minus 1.5 standard deviations, and the right value the average plus 1.5 standard deviations. So we can assign these curve shapes to the actual distribution of statistics. And as the statistics evolve without human intervention, these scoring curves can change shape without any human intervention. So there's also a decline curve where we say low is suspicious. So maybe this could be something like if you are a general practitioner and you do no teeth cleanings at all, that makes no sense that there's no teeth cleanings done in a general practitioner dentist, where a high number of teeth cleanings might not be suspicious, because we would expect the general practitioner dentist to do a high number of teeth cleanings. Or if you're a medical doctor, we would expect the medical doctor to write a lot of antibiotic prescriptions because people get infections. But if you were a general practitioner and you did nothing or did very little of something compared to your peers, that could be suspicious. So that's in a case where a decline curve could be suspicious. There could be a case where an inverted bell would be suspicious, where a low number would be suspicious and a high number suspicious. This might be the number of days since the beginning of the insurance policy. So if you have an annual policy, if you file the claim on day 1 of the policy, you had an auto accident on the first day of your car policy, that might be suspicious. Or if you had a car accident on the very last effective date of your policy, that could be suspicious, where an accident in the middle of your policy life would not be suspicious. So this is an example of a way we could assign an inverted bell curve, or then another would be a bell curve where the average is suspicious. There's 4 curve types. So we could parameterize the curve types with 4 parameters, choosing the type of the curve, choosing a left, mid, and a right value of the curve. We can parameterize the curve with these 4 values, and these 3 of the 4 values could be assigned to the statistical distribution of the curve and calculated automatically from the modes of the statistical distribution without human intervention. So that's the typical setup. And typically, we would interpret these curves to say, if a specific entity has an attribute value which is very different than all of its peers, then it could be very suspicious. So that's that growth curve, or the bell curve. If you're very different than your peers, you're in the extremes, then that's very suspicious. If you're only a little bit different, or somewhat different, then that's moderately suspicious. If you're a little bit different, that's a little suspicious. If you're not different, then it's not suspicious. So that's the shape of those curves. That's how you interpret the curve. A low value 0 means you're not different than your peers. It's not suspicious. If you're a high value, a growth curve, you're right on the left extreme, you're the 99.9th percentile, then you are very different than your peers, and that's very suspicious. But one feature in and of itself is not sufficient to determine whether a person or a claim is suspicious. So we need to calculate thousands of features. So the theory here being that if one feature has a 99% false positive rate, then obviously one feature is not good enough. But if you had 1,000 features and each of those features was completely independent, had no relationship with each other, so they were linearly independent, then 0.99 to the power of 1,000. Let me put that in my calculator and see what that spits out here. 0.99 to the power of 1,000. And that would be 0.0004. So that would be 4 to the power of 4 times 10 to the negative 5. So 1,000 linearly independent features, even if each of those features was 99% false positive rate, if you put 1,000 independent features together, your false positive rate drops to 0.00004, right? So that's the theory. Look at thousands of features compared across peers and score them using those types of curves. And now the reinforcement learning setup is, if you imagine the first curve, E is the entity. Now we could do this at the claim level. The claim could be considered an entity. Any of the people associated with the claim, so each person could, at the person level, a person is an entity. You could consider the address that the claim happened at an entity. So you went to a clinic, there was an address at the clinic, that was an entity, or the address of the person, that's an entity. So there's an entity hierarchy associated with the claim. It could be the practitioner, could be an entity at the dentist or the doctor, could be the clinic or the hospital. That could be an entity level, or it could be a social network. That could be an entity, the group of people. So we can score and calculate features at the entity. So at the claim, the features could be the dollar of the claim, the procedure of the claim, time since the previous claim happened, could be all the different elements like the lab fees if you had a medical test done with the claim. So you could create thousands of features from a single claim record. And if you aggregate the claim record up to a person, it could be how many claims did the person have in a month? How many claims of a certain type did the dentist do in a month? So then when you aggregate it up to a practitioner, this becomes the billing behavior. Could be counting the frequency, could be looking at the dollar amount, could be looking at the percentage distribution of the one procedure type over all procedure types. So this is how we can calculate thousands of features, even from a simple claim record that might have 50 attributes. So here we would sum, so the VI is the individual feature value. The 4-parameter F is the fuzzy logic curve. So F0 would be the curve type, a growth, decline, bell, or inverted bell. Then the 1, 2, and 3 superscript F would be the parameters of the fuzzy logic curve, the left, mid, right value. Each variable feature I has its own curve. So each curve is parameterized. Each variable feature has a type 1 fuzzy logic membership curve that's parameterized by 4 values. And we can then aggregate those features. If we had 1,000 individual features, we can aggregate them up to give one score at the entity level, or we can give a number of scores at the entity level. We could categorize them by billing behavior, like frequency, dollar, distribution. We could have a number of concepts. So the FJ are aggregation functions, and we wouldn't simply average the features, because simple averaging doesn't work. If you had 10,000 features and 99.9% of them were normal, had a 0 score, the average of 10,000 numbers when only 2 are non-zero would still be a low number, and you would get a low suspicion. So you'd have to do some more sophisticated fuzzy averaging. So once you had fuzzy scores, a way to aggregate the fuzzy features, and you could assign a scores at the entity level, we can then cluster the entities based on whether they are outliers or not. So this reward function is the Condorcet criteria. If you look up Condorcet on Wikipedia, it is a way of clustering records. So it's a very simple cluster. So we can compare if record I and J, so this is entity I and J, if person I and J are in the same cluster, then we would expect that the difference, delta ijk, would be for the variable k, for the feature k, do they have a different value? If 2 people were in the same cluster, you would expect that for feature I, they would have the same fuzzy score if they were in the same cluster and had the same behavior, right? So we would expect individuals or claims or social networks in the same cluster should have the same feature value. So we would expect delta ijk to be 0. 1, if you're in the same cluster and you have the same value, then that contributes positively the ratio. Same variable value, same cluster. That means that's a good thing for clustering. If you're in the same cluster but have a different value, Sij is 1, different value 1, this doesn't contribute, this comparison doesn't contribute to this value. So if you're in a different cluster, you have a different value, Sij is 0, different value is 1, -1 squared is 1, that contributes positive value. So now we're comparing all the fuzzy feature scores for each entity across all features, across all pairwise combinations of entities. That's the n choose 2, n times n minus 1 over 2 is the number of comparisons times k, the number of features. We can sum all of this up to assign a clustering to say, is this clustering is good? We can assign individuals to clusters. And we can limit the number of clusters. We want to find the most different individual clusters, the most distinct clusters, so we want to maximize this Condorcet criteria, choosing the parameters, the reinforcement logic. Now, the reinforcement learning algorithm chooses the F parameters, the feature type, the curve type, and the curve parameters, such that we get the largest number of distinct outliers, the number of clusters that are more different than the peers. And this is what we want. We want to find the most outlying entities that are the most different than the peers, and that would be reflected in the Condorcet score. This parameter would have a value between 0 and 1. The closer it is to 1, the better of a clustering it is. And if we limited, let's say, just to 2 clusters, outlier and not an outlier, we would want the largest number of outlying records that have the highest Condorcet score possible, and that would be the reinforcement learning reward function. I didn't put here the count of records would be the second part of the reward function, where we would have a weighted function that would be a function of the Condorcet criteria plus the number of records in that outline cluster. So that's the reinforcement learning setup, and we would choose the parameters Fi with 0, 1, 2, 3, choose those parameters that result in the most distinct outliers. We would do this. Every new record that comes into the system automatically changes the scoring curve shape, and we can run the reinforcement learning continually as every new record runs in the system, and these curves tune automatically with no human in the loop, because we know that all outliers are fraud, especially if you're monitoring thousands of features with hundreds of peer groups doing billions and trillions of comparisons, which is beyond human ability. We can find that 0.99 to the power of a billion is 0. The likelihood of being not fraud when you have multiple features, multiple peer groups, and we're tuning this automatically, is likelihood is 0. A fraudster cannot manufacture a normal looking record because they don't know the statistical distributions of all the data that goes into the fuzzy logic system. So this is called type 1 Mamdani fuzzy logic, the reinforcement learning setup, where we're automatically choosing the fuzzy scoring parameters to choose outliers. And so now we can create fuzzy logic rules in the context of this. We can say the way we choose the fuzzy aggregation functions which is another part of the reinforcement learning setup, is choosing these with the way we aggregate fuzzy scores. So we would want to say a dentist that has many metrics with high suspicion, then investigate. So if you've got a lot of features that have a high score, that's a no-brainer. This person is an outlier on many, many things. They're billing a lot. They're seeing more patients than everybody else. They're doing more of a certain type of procedure than everybody else. So if you have lots of metrics that have a high score, right? If you have a few metrics that have a moderate and a high score, then don't investigate, right? If most of your features are not high, then you don't need to investigate. If you have zero metrics, so few is a fuzzy concept, right? So we apply a fuzzy curves to many is a fuzzy concept. All the underlying terms here are fuzzy concepts. You can apply fuzzy curves to the words as well. If you're familiar with type 1 fuzzy logic, you can see that these are typically polygonal type curves or linear curves, where we can apply a fuzzy definition to the linguistics. So if you had a few metrics that had a very high suspicion, then you should investigate, like this person is billing more of this high value root canal than all other practitioners who do root canals. That should warrant an investigation, even though it's one metric out of 10,000. That would warrant an investigation. Or if you had many metrics that were a little bit suspicious, so the fact that you accumulated a lot of behavior that was a little suspicious, that should be enough to warrant suspicion. And now we use fuzzy curves to define many, little, some, moderate, high. So it's not just an arbitrary 900 is high. We can apply a fuzzy curve to the concept of zero, few, many, some, low, moderate, high. So each of these linguistic terms has one of those curves. It could be the growth curve could be applied to the concept of low, moderate, high, and the concept of zero, a few, many could also have that growth curve applied to that concept. And so those we could, again, make those parameters that define these words as parameters of the fuzzy logic system. Now we're looking at, that's how we score the entity. So we take all those fuzzy curves that have been tuned on the previous page here. Now we have a fuzzy tuning that say this suspicious scores generates the most outlying individuals. And then we can further score the individuals with to say, does this individual have a few metrics that have a high suspicion? We can overlay this on top of the clustering to say, this is how we assign an individual score, that this person gets 1,000 is their suspicion score because they had a few metrics that had a very high suspicion based on the previous scoring. And that would be a cluster that's very different than the average cluster of providers that had a few metrics of high suspicion. So that's how we do peer analysis. So using rules, we can apply rule scoring to the system. So an if then else rule could be, if you go to the dentist for a teeth cleaning and you get a emergency visit, that would be an example of a simple rule. And that's an if then else. If you break the rule, you get a value of 1. If you don't break the rule, you get a value of 0. So that's a basic rule. The downside of that is that there's a lot of false positive with rules. So we could apply a more probabilistic notion to that. For example, a rule like if you see your chiropractor 3 times in the same week for the same condition, that could be 1-0 binary rule. We might want to fuzzify that to say 3 was an arbitrary choice, 7 days was an arbitrary choice. We can say, create a fuzzy rule that says, the more frequently you see a chiropractor in a short period of time for the same procedure, that would be suspicious. So by fuzzifying the rule, and again, applying a fuzzy growth curve to the rule, we can apply a continuous score to the rule. So the rule gets a score between 0 and 1,000. So we can fuzzify binary rules with arbitrary thresholds and apply the fuzzy logic to the rules again. So now a rule that used to generate binary scores, we can now have a fuzzy output. And you could have hundreds of rules that you apply today that we fuzzify and lower the likelihood of a false positive rate and treat rule breaking as just another feature. So that becomes just another peer analysis feature. So everything becomes part of peer analysis. The number of times you break a rule, the number of different rules you broke, we can apply a fuzzy scoring parameter to these, as well as to the rule itself has a fuzzy scoring curve. So now we're using rules as just additional features that we're putting into the peer analysis of different type of variable features. So not just the number of times you did a procedure, but now the number of times you broke a rule and the fuzzy score associated with that rule breaking behavior. We can also mine for new rules by looking for statistically odd rules. So we can run association rule mining across the rules. We can say what procedure codes go together. So here's an example of some negative lift rules for dentistry. So we can go, if you've done rule 02601, which is radiograph single film, plus 4 units of scaling, so you get your teeth cleaned and some x-rays, that negatively implies a limited examination for new patients. So you wouldn't get teeth cleaned and x-rays for a new patient visit on the same day. That's not typically what you do on the same day. So this occurs only 0.01% of the time with low confidence of 25% and with a negative lift. Lift of 1 means statistically normal. Lift less than 1 means these things are negatively correlated. So here's a low lift rule that's negatively correlated. These procedures shouldn't go together. So if we found these procedures together in a visit, this tells us this is statistically anomalous. So again, we can apply a fuzzy logic curve to this rule to score these procedures occurring together. And similarly, there's another rule there, root planing periodontal with 4 units plus root planing half a unit negatively implies a limited diagnosis for a new patient. So you wouldn't get your teeth cleaned or done scaling on a new patient visit. This occurs 0.02% of the time with a negative lift of 0.6. And again, this is an opportunity for a negative rule. Again, we can apply fuzzy logic to this. And so we can automatically mine for new rules just by looking at which procedures belong together and if they occurred and which procedures don't. And so procedures that don't belong together can automatically trigger new rules. So we can continually be mining data as it comes in for low confidence, low lift or negative lift rules. We can also be looking for high lift rules. So things that always belong together. So if you get x-rays for a certain joint with 4 films and you get a tomography done, I'm not a dentist, so I don't know what tomography is. You get tomography done, 4 views, these go together 2,000 times more than statistical expectations. So the fact that these belong together when they are not together, that's just odd. So if you see one without the other, that's an example of things that's odd. That could be that somebody trying to create a fraudulent claim, not understanding dentistry. Similar example there, 3 diagnostic photos implies additional photos over 3. So if you're doing more photos, typically more photos over 3 and 3 photos would go together 1,600 times more than random coincidence. Again, if you saw one without the other, you would say that's suspicious. You saw the additional photo over 3 without billing for the first 3, that would be odd. And again, without knowing anything about dental or medical practice, we can just look for statistically anomalous things that always belong together that aren't occurring together, things that shouldn't belong together that occur together. We can mine for these rules, apply a fuzzy curve to that. And again, these new types of rules just become another feature that we apply to peer analysis. Then we can do predictive modeling. So your standard supervised learning using labeled training data, where we have historical labels, fraud, not fraud, pay, not pay. And we can use our supervised learning like deep learning or random forest or NARIX or support vector regression, any one of those methods. And we can apply predictive models. We can automate the predictive modeling process so there's no human in the loop. We can just build new models with new labels as they occur in the data. And we can assign a predictive modeling score. And again, we can assign a fuzzy logic curve to predictive modeling score. So if we built 100 predictive models on an individual claim, that just becomes another feature in the peer analysis. So the fact that every claim has typically 3 predictive models that score high, well, that's not interesting. How many predictive models scored high? If you did 6 predictive models scored high, that's an outlier with respect to the average of 3. We can now interpret predictive models in a different way. The number of predictive models that scored suspiciously compared to the average, or the number of high scoring predictive model records compared to the average. So we can apply a growth fuzzy logic curve to the predictive model scores. And again, it creates predictive model scores as just yet another feature to feed into peer analysis. Right, and now we can do social networking. Are we linking people together non-obviously? So 2 people who are in the same family, they share the same system ID, they have the same address. Well, that's not interesting. you're in the same family, we expect you to live at the same address. But now, if you're in a different family and you don't live in the same address, well, that's suspicious. So here's an example. If we look at the bottom, there's 4 claims there, occurred one day apart, same procedure, same dollar amount. And if we look at just the top row of personal information, well, those look like 4 different people. Now, if we have all the variations of personal history, we can see, oh, look, Catherine, Kate Green, and Kate Grundig, there's some common. They Kate, Catherine, Groindig, the name. We can see some of these records are connected, similar names. We can look at similar addresses. Record 1 and 2 have the current address and an old address match. We look at record 1 and 4, current address and old address match. We can look at record 2 and 3, the addresses match with the transposition of the street number. We can look at the PO box between record 3 and 4, current address, previous address match. We can look at date of birth between record 1 and 4, the month, year, or month, day is transposed. Similarly, between record 2 and record 3, the month, day is transposed. And so by doing that, we now have come to the conclusion that 1, 2, 3, and 4 are all the same person. So doing identity resolution, then we can say if 1, 2, 3, and 4 are all the same person, then we conclude that the 4 claims that look like different claims are actually the same claim. And we would deny all of this because the same person submitted the same claim 4 times. So by doing identity resolution, which is part of social networking, by resolving identities and eliminating people playing identity games, making sure we keep track of all the different versions of personal information we have, because it's in those different versions that we find people using tidbits of truth. You cannot manufacture personal information, addresses, birth dates. You have to have some kernel of truth. So looking at all the historical variations, we can do identity resolution. Similarly, we can look at the relationships between people. Here we can see Kate Green and Quan Kim have the same address, yet they're not in the same family group. Okay, well, that's an odd connection. Why do these people have the same address? We can look at person 3 and 4. They have the same phone number, but they're not in the same family group. That's a non-obvious connection. We can look at person 2 and 3 share the same bank account. Why would they have the same bank account if they're not in the same family? And now all 4 of these people having a root canal. So the 100% of people in a network of 4 who are connected non-obviously with the same address, same phone number, same bank account, yet they're not in the same family group, having 100% of people in a 4-person network all having root canals, that is an outlier. So again, we do an outlier analysis on the social network built from non-obvious connections. And what would have looked as 4 root canals and 4 unrelated people, that's not an outlier. But when we relate them to the same network, because they are non-obviously connected, now the 100% of a network having a root canal becomes an outlier. So we've assigned a fuzzy logic curve to the procedure code root canal to a network that we built linking people non-obviously. So again, social network behavior aggregated to the social network, we can apply fuzzy logic curves and we can determine, again, is this network an outlier or not with respect to its peer networks. So I've walked you through how we do that. Social networks, we use ant walking methods to grow social networks, and I'll talk about that another time. Ant walking itself is a fascinating story. I may have mentioned this in a previous podcast, but ultimately that's what DAISY does. There's some of the math behind using reinforcement learning to choose fuzzy logic curves in a fuzzy logic system. What normally is thousands of features create a 1,000-dimensional space. And if you're a statistician, you know that doing outlier detection in a 1,000-dimensional space, the distance between data points is every point is an outlier when you have a high dimensional space. So this is the curse of dimensionality. By reducing everything, projecting it all back to a type 1 Mamdani fuzzy logic space where we have one suspicion curve space, and using reinforcement learning to choose the membership functions and using different aggregation methods to aggregate those fuzzy logic scores, and applying peer analysis using Condorcet clustering as the reinforcement learning reward and counting the number of distinct outliers, we can build a reinforcement learning system that has no human in the loop, and we treat rule breaking, apply fuzzy logic curves to rules, apply fuzzy logic curves to predictive modeling scores, and apply fuzzy logic curves to social network behavior aggregated to the social network level. We do peer analysis on all of that. We can find highly suspicious individuals, networks, claims, and do fuzzy logic that way with very low false positive rate. So that, in summary, is our talk about reinforcement learning applied to an outlier detection system using different methods of analysis to create a high suspicion score. And we can do the same. I'll talk another time about doing this with payability. We can create a high payability index using all the same methods. We can create high risk index, looking at quote data or incoming data for quotes to get a risk index, and we can use that for risk rating. So hopefully that's a long-winded introduction to AI and insurance. Thanks again for joining. As always, subscribe on Spotify or YouTube to our podcast, and I welcome questions and feedback about this. If there's anything, don't hesitate to reach out. Thank you so much.